Today, we're going to compare mTLS and HTTP message signatures. So our customers often have to decide which one do they use, mTLS or HTTP message signatures, because in some cases we support both of those. So in this video, we'll go over the pluses and minuses and some details of both. All right, so let's start with a brief intro. HTTP is the backbone of modern system communication. And over HTTP, you communicate with your server. The server has to confirm if it's talking to the device that was enrolled, not some bad actor or some imposter. If you're using microservices, this extra authentication lets you recognize a real microservice. So both mTLS and HTTP message signatures are powerful and secure, but they take different approaches. mTLS is baked into the TLS handshake. It is tightly and deeply integrated with TLS, while HTTP message signatures are more explicit and flexible. They wrap the HTTP messages in extra crypto. All right, let's start with mTLS. What is mTLS? We did a video series on mTLS, which will be linked down below, that goes into more detail, specifically about building an mTLS client using the system key store. All right, back to mTLS. So ordinary TLS, transport layer security, only the server presents the certificate to the client, right? You've got the client hello, and then the server sends a hello and the certificate. So this way, the client knows that the server is legit. In mutual TLS, the server also sends a request, hey, I want your certificate. And the client then sends its certificate. So this verification is mutual. Both the client knows that the server is legit and the server knows that the client is legit. So mTLS is built into the TLS protocol 1.2 and 1.3, and it is fast, right? It is handled largely at the OS level. OS knows how to do it. The browsers handle it. And it's also used internally for like internal service meshes, Kubernetes clusters, even secure databases, and then private APIs, right? Point-to-point private APIs. And it's because it's built into the TLS, it's not just for HTTP, right? It's for other traffic, gRPC, etc. Like I mentioned, database connections that go over TLS can use it. All right, so what are the pros and cons of mTLS? All right, the pros, like I said, it is built-in support across OSs, browsers, web servers. There is the strong identity baked into the connection itself. So you don't need necessarily extra identity verification, right? You can even use it in some cases as your main way to identify your client. For example, if you issue your client a very specific certificate and that client's got the private key, right? You know the identity of that client. There's no need to change application logic, right? As long as your application supports TLS. If you update your server to mTLS and make sure your client has the cert, then it's possible that you may not need any actual application changes. It does have broad integration with native certificate stores. Think macOS Keychain. However, if your specific application uses mTLS and your specific applications needs to rely on the certificate store, then you may need to implement your own integration, right? So it's not, if you want to integrate your certificate stores, you probably need some extra work if you've got your own app. All right, the cons of mTLS. Well, one of the major cons, it is hard to scope by endpoint, right? You can have like a login endpoint, a health endpoint, API read-write endpoint, etc. It is hard to say that this endpoint is mTLS and this one's not. Typically, you either want to enforce mTLS for your whole server or not. So it makes mTLS not very flexible. Also, TLS termination is an issue because with mTLS, wherever you terminate the connection, that termination needs to understand and enforce this client authentication, right? It needs to know about the client certificate. It needs to know about the client certificate. So think there's a layer between the server, your ultimate server, like a load balancer. So it needs to parse this client certificate, authenticate it, and then pass this information to the server. So like I said, now like I mentioned, load balancers. So load balancers, it's standard practice to terminate the TLS connection at your load balancer, right? So then you have to have like extra configuration, extra logic in your load balancer that you then pass into the server. And that's kind of inconvenient for application developers. For example, we allow our customers to run on-prem, right? But we don't know what load balancer they're running. We can't possibly support every load balancer out there. So mTLS is not great for public APIs. Many clients, maybe mobile apps, some SDKs may not be able to handle client certificates. So it may be difficult to adopt mTLS in certain environments. All right, we talked about mTLS. Let's talk about HTTP signatures. Let's get to our sequence diagram here. Message signatures, kind of precisely what they sound like. You take an HTTP request, select a few headers, maybe a body, and then sign them with a private key. And then server needs to have the public key, so it uses the public key to verify that signature. All right, let's look at this sequence diagram. So the client needs to have a private key. It can generate one or retrieve one. Client needs the private key, server needs the public key. Then HTTP request is generated. Basically, one issue here is kind of, you might need to buffer this, right? You might need to buffer the entire request before you process it and sign the headers and body. You sign, you send it to the server. The server needs to associate this request with a public key. So there's so you need some logic to figure out how to associate the signature with the public key. It extracts the signature and any headers and verifies it. And then if they're valid, it processes the request. If not, it rejects. Now it's possible to do the signing both ways. So it's possible when the server sends the response back, it could also sign it. So that's an option to have an HTTP signatures go bidirectionally. So as you can see, HTTP signing works at the application layer. So it does not replace TLS, but rides on top of it, right? So you could still have TLS. You can even have mTLS. So you can have both mTLS and HTTP message signatures. So what does this mean? This means, since it's application level, that means you don't need to worry about this load balancer configuration. You don't need to worry about where TLS is terminated or kind of what the proxies are doing between your client and your server. All right, because you know at the end, you will be able to verify that signature. All right, so many legacy systems have their own approaches to HTTP signing. So currently, HTTP signing is not as standard as TLS. For example, Apple's device management protocol relies on a detached CMS signature with a custom header. So CMS signatures are a standard, a generic standard to kind of sign arbitrary message content, right? So Apple signs the body, and then it adds the special MDM signature header. So it's not completely standard, but also at the same time, it does use a standard as part of the solution. GitHub, on the other hand, uses HMAC-based payload signing. So HMAC is hash-based. So it has a shared secret between the client and the server, and then it uses the hash-based signing to sign the message, and then the other side using the same secret can verify the signature. But these mechanisms take a different path to the same goal, verifying the integrity and the origin of your HTTP messages. So the good news is today there is a proposed standard that a lot of the modern systems are starting to align with, and it's RFC 9421 that takes a lot of the concerns and tries to standardize them. So the ecosystem is gradually converging on this standard, and of course it's beneficial to use a common standard when you don't control the client or want some kind of standard auditability and control over your HTTP message signatures. So using this standard, I'll give an example of our signatures. That's a screenshot of a video demo I did. So you've got the content digest over here. That is the digest of the body. Not necessarily part of the signature, but oftentimes the way you do signatures is you take a SHA-256 digest and sign that. In this case, it's the content digest of the body. Then you got these two headers. You got the signature itself, and then you get the signature input. So signature input is like the metadata for the signature. So here it tells you what's being signed. The method, post, authority, that's the host, path, that's like API v1, blah, blah, blah. Query, any query parameters, and content digest, which is the digest of the body. There's some additional metadata. This key ID is being used for the server to know which public key to use. It's got a created date here, and the thing you're not seeing is the nonce. So I'll talk about the created and the nonce a little later. All right, let's talk about the pros and cons of HTTP message signatures. So pros, you got the fine-grained control, right? You can sign specific API paths. For each signature, you can select which headers and which body fields to include. For example, some requests may have a content type and some requests may not. So for those requests, you may choose to sign that content type to add additional integrity protection to your message. So fine-grained, very flexible, right? Then, as I mentioned, the signature verification works independently of TLS termination. So you don't need to worry about proxies or load balancer. You just need to worry about your application, right? Your client and the server, and you don't need to worry about the stuff in between. Also, HTTP message signatures, they don't require certificates, right? mTLS requires certificates, but HTTP message signature can just rely on private public keys and don't need that whole certificate infrastructure. That said, you could still use a certificate, right? You can still use the same kind of certificate flows you've used with mTLS and just use that certificate for HTTP message signatures. Because, like we saw, you can debug it easier because you can see the signature input, content digest. You can see that in your normal traffic. So it's easier to log and inspect the signature and debug. You can also integrate it with your system key stores, whether you're using TPM or macOS Keychain, but that needs to be done by your application. And another pro is because it is becoming a standard, there are signing and verification libraries available for it. So you don't need to roll your own solution. like legacy systems like Apple and GitHub have done. All right, what about cons of HTTP message signing? So you have to integrate, even though libraries are variable, you have to integrate or create, if you're doing something weird, you have to integrate or create the signing logic instead of relying on TLS or your OS. Another issue is you must manage replay attacks, and I'll talk about those a little later. And then this flexibility also comes with a cost, right? You have to choose which headers, which body you want to sign. And the fact that it's so fine-grained means that if you like change something, how your signature is done, you may break interoperability. Or even worse, you can break backwards compatibility. If your client's been updated, it like changed how the signature is calculated, and then the server for some reason can't handle it. All right, next let's talk about performance considerations. So like I mentioned, mTLS is fast, it's built in. This authentication step happens once per connection during the TLS handshake. And its benefits from all the TLS acceleration and session reuse magic that your OS and hardware provide. Of course, you have to rely on the session reuse. Like if you send a request once per hour, you have to make sure that sessions are being reused for maximum speed. HTTP message signatures, however, happen every time. So every time you have to run the crypto, right? You have to sign the request. You're still running TLS most likely. So you've got crypto with TLS, and then you've got another layer on top of that. So this means more CPU cycles, especially if your implementation isn't careful. Or you aren't using the most efficient algorithms such as ECDSA. And like if your headers are huge, your bodies are huge, that could be a performance cost. But for most APIs, performance isn't really dominated by the CPU cycles. It's more likely dominated by network and I/O. So unless you're operating at very high scale or your devices are constrained by the amount of CPU they have, in that case, the performance difference between mTLS and adding HTTP signatures is probably negligible. All right, next let's talk about replay attacks. So what's a replay attack? So a replay attack occurs when a bad actor captures a legitimate request, right? Like the one we see. So a bad actor captures this, and you can see, I can do that right here. I can just get all the headers, get the body. And then replays it later. So basically send the same request to the server again. So think resubmitting a money transfer or resetting a password, right? Those things you don't want to be getting multiple times as a server. So how does mTLS help with this? So mTLS helps it by tying its authentication to its TLS session. And in order to create this TLS session, you need the private key of the client. So an attacker can't simply replay a captured request from another machine because they need to create a session, and in order to create the session, they need the client's private key. So fundamentally, mTLS stops early on. It prevents the attacker from making a connection in the first place, right? So what does this mean? Well, that means mTLS prevents a connection from being made, but mTLS alone doesn't prevent replay of application layer data, right? If the attacker somehow modifies your app or on your device replaying the attack, so it doesn't prevent against that. But those cases are extremely unlikely, right? Your whole machine is probably compromised at that point. All right, how do HTTP message signatures handle this? Well, they basically require to build your own defenses. Although the spec that I mentioned has things to help with that. It's got the created at, it's got the created, and it's got the nonce. So let's search created parameter, right? It's got creation type as unique inclusion of this parameter is recommended, nonce, a random unique value. So these two, created and the nonce, are there to help you prevent replay attacks. Because it's more in the clear than mTLS, right? The client just needs to verify the server is legit. So it's easier to try a replay attack when only HTTP message signatures are used. So those two values, how would you use these? So here's an example of how you'd use these. So, one thing you can do is you can look at this created timestamp. And you can say, you can just check, for example, if the server is within 1 minute of that created timestamp. And the reason that it works is this created timestamp is part of the signature, right? So we know this timestamp is valid. You could combine both of these. Maybe your clients are, their clocks are not accurate, right? You can combine created and nonce. Nonce is just a random value. So for example, first you check that created is within 10 minutes. So maybe you broaden the time here. You say created within 10 minutes. So we do this check. Then we also check the nonce to make sure this nonce has not been used within the last 10 minutes. So we do a combination of created and nonce. So you can use like a cache with expiration, like Valkey or Redis, to store your nonces. So a little bit more infrastructure, right? You got an extra request to your cache, but you've got replay attack protection. All right, let's summarize what we talked about. How do they compare mTLS and HTTP message signatures? Let's scroll down to my table here. Make this bigger. All right, identity verification. We got the client serves for mTLS. We got the public key for HTTP message signature. Integrity, right? It's built into the TLS. So everything going across TLS, we know it's valid. HTTP message signature, we customize, we tell it, in the signature, we decide what is valid, right? Which headers are valid, which body is valid. So that means if a proxy like adds a header and then makes it to the server, that new header, if it's not signed, then the server cannot rely on it. Granular control, right? You typically use mTLS for your whole server. It's very hard to apply it per route. HTTP message signature fine-grained, very easy to determine what's signed, what's not, things like that. Deployment complexity. mTLS high, it does require certificates. It also requires mTLS-aware proxies or load balancers. HTTP message signatures, deployment complexity is a bit less. Instead of certificates, you just need keys. You can also use certificates, but you don't need to worry about this TLS termination. Can you use it for public APIs? Very hard to use mTLS for public APIs. A lot of the use cases are internal. HTTP message signatures, yes, definitely being used for public APIs even right now. Certificate handling, this kind of a repeat, yes, it requires a cert. HTTP message signature just needs a public key, does not need a full cert. Integration support, mTLS has existing OS browser support. Message signatures do not, but maybe they will in the future with the standard. But application software libraries are available for you to integrate with the RFC 9421. Replay protection, all right, it's kind of, you get it for free almost, because the attacker needs the private key unless they're already on your machine. HTTP message signatures, you kind of handle it. You need to create additional logic to add replay protection. Performance fast. HTTP message signatures, we cannot say it's fast, but it may be negligible depending on how much traffic and how big of things you're signing. Debuggability. If mTLS is not working, then you got to go into the into Wireshark, all those types of tools to try to debug it. HTTP message signatures, a bit easier to debug. All right, so which one do you use? Use mTLS if both ends under your control, right? You've got internal traffic, preferably without load balancers. It's fast, OS integrated, well supported. Use HTTP message signatures. When you need finer grain control, like per request control, we want some requests to be signed, some not. You kind of want more flexibility. Or you operate in an environment where you don't want to use certificate management. Fine grain control and debuggability, right, for HTTP message signatures. High performance if you're like sending a lot of traffic. mTLS is better as long as you can handle the more complex setup. And just to note, it is possible to have both. You can have both mTLS and HTTP message signatures. So, different tools for different jobs, just don't skip authentication. Thanks, everyone.